Welcome to our explainer on the intriguing, absolutely head-spinning concepts from the source material Immeasuracy 18. I'm getting dizzy. Today we're taking a chronological road trip to see what actually happens to our math and our physical reality when we just try to change direction. Sounds pretty basic, right? But as you're going to see, the mechanics and the arithmetic behind simply turning around are way more fascinating than you might think. Imagine you're moving forward, and suddenly you decide to just head back to where you came from. You'd probably think it's an instant action, right? Just a quick pivot and boom, you're on your way. Well, let's dive right in and break down literally every fraction of a second of this maneuver to see the true mechanical reality at play. Section 1. The setup and the spin, leaving point O. So, our journey begins right here at point O. We're traveling perfectly straightforward toward a destination called point P, moving at a nice steady speed of 1.0 meters per second. But then, suddenly, we decide we want to look backwards, aiming for the exact direction we just came from, a full angle pi away. Here's the catch, though. Spinning isn't instant. We can't just magically teleport our orientation, right? The source material lays out that it takes us exactly 0.3 seconds to physically spin around and face backwards. Time is literally ticking while we rotate. Now, this is absolutely crucial. This rate of turning, it becomes a completely new unit of measurement for us, which we call angular speed. Since we just turned an angle of pi over the course of 0.3 seconds, our average rate of spinning gives us an angular speed of negative 0.3 pi per second. So we've basically got a brand new way to measure our movement. Moving on to section 2, the mechanics of turning, the axis of rotation. So to fully describe a spin, just having the speed actually isn't enough. We also have to specify the direction, the azimuth and altitude, of the axis we're rotating around. Since we're traveling on a flat, horizontal plane here, we're naturally turning around a vertical axis. And mathematically speaking, choosing a positive or negative altitude for this axis is purely a convention. If we spin leftwards, counterclockwise, it's an altitude of half pi. If we spin rightwards, it's negative half pi.
To determine that convention and really visualize it, do me a favor and hold up your hand right now. Yeah, do this with me. If we stick our right thumb up into the air, you'll notice your remaining fingers naturally curl and point leftwards. This physical relationship perfectly maps out our spinning direction relative to our axis.
And that right there brilliantly illustrates what's known as the right-hand rule. It applies to all sorts of rotations. Try it out. If you point your right thumb towards the left, watch which way your fingers curl. They curl downward, simulating a forward flip. Now point your thumb to the right, and your fingers curl upward, exactly like a backflip. It turns out your own hand is a perfect little model for rotational physics. So, to summarize our spin so far, the axis direction we just found using our thumb, combined with the angular speed we calculated earlier, those together make up our angular velocity. It behaves just like a standard vector, although, fun fact, mathematically speaking, it's actually classified as a pseudovector. All right, section 3, the resistance, changing angular velocity. Let's see how all of this builds into that actual physical resistance you feel when you try to alter that spin. Because changing angular velocity is definitely not a free action. Here is a really fascinating parallel for you. Just like it takes time to change your forward speed when you hit the gas or the brakes in a car, changing your angular velocity takes time. Why? Well, it's because we possess a property called the moment of inertia. You can think of it as the rotational equivalent of mass. It's basically the stubbornness of an object to resist any changes to its spin. And the rate at which we finally overcome this inertia to change our spin, that's called angular acceleration. Much like angular velocity, it's also a pseudovector, and we measure it in units of pi per second squared. Essentially, we're constantly fighting against this inertia to alter our movement. Which brings us to section 4, the brakes and the return, calculating the U-turn. Let's get back to our road trip. Remember, by the time we actually finished that 0.3 second spin, we hadn't just stayed in one place. We'd actually moved 1.3 meters away from our starting point O. And now we finally decided to return. We want to move back towards O, but we've got a major physics problem first. We're still moving forward. We literally have to hit the brakes and decelerate first, which, you guessed it, takes even more time. So here is the mathematical puzzle our source presents. If our deceleration rate is 0.7 meters per second squared, how long exactly does it take us to come to a complete stop from our original speed? The answer, remarkably, is exactly 0.3 seconds. But how we actually get there? Well, that's where this source material gets highly unusual. Using the author's unique immeasuracy arithmetic to find the time, we have to divide the speed unit by the acceleration unit. But in this completely bizarre framework, we do that by simply subtracting their magnitudes. So 1.0 minus 0.7 gives us exactly 0.3 seconds. No prefactor required. According to the text, this is literally the correct way to calculate it within this system. Now, during this 0.3-second braking period, our average speed was half our initial speed, meaning it was 0.7 meters per second. And because we were still moving forward while hitting the brakes, we ended up traveling an additional 1.0 meter further away from point O. Okay, so we've finally come to a complete standstill. Now we have to accelerate back towards point O at that exact same rate of 0.7 meters per second squared. By the time we get our speed back up to 1.0 meters per second, guess what? Another 0.3 seconds has passed. At this point, we can just coast the rest of the way back to O. So let's tally all of this up on our timeline, because it's quite the sequence. It took us 0.3 seconds to spin around, another 0.3 seconds to hit the brakes and decelerate, 0.3 seconds to accelerate back towards our origin, and finally 0.3 seconds to coast back to O. Now, staying completely true to the fascinating mathematical logic presented in our source, we have 4 distinct segments of 0.3 seconds. In this specific arithmetic, 4 times 0.3 calculates out as, wait for it, 0.6 plus 0.3, giving us a grand total of 0.9 seconds for the entire round trip. The author absolutely notes that it takes a minute to get used to this highly specific style of arithmetic, but hopefully seeing this step-by-step breakdown makes these numerical manipulations feel just a bit more intuitive. It really asks us to entirely rethink how numbers combine. This chronological journey gave us one incredibly fascinating step-by-step way to return home, but it definitely leaves us hanging with an exciting question to wrap up on. If this was just one strategy, what entirely different mathematical and physical maneuvers are we going to have to use to get back to O next time?